Faultcalc.xls Spreadsheet, authored by John Sokolic, is designed for short-circuit calculations in 120/240 volts, one-phase systems. It's important to know that this file is no longer available in the free stuff section of the website. Regarding accuracy verification, without access to the spreadsheet, commenting precisely is challenging. However, some observations can be offered. It is not typical for the short-circuit value to increase when moving point-to-point downstream in line to neutral calculations. This suggests a potential error in the spreadsheet formula or its logic. The removal of the spreadsheet from the free stuff section could mean the author or website administrators found errors or have concerns about the file. If you're worried about the accuracy of Faultcalc.xls, caution is advised when using the spreadsheet for critical calculations. It's a good idea to verify the results from the spreadsheet with other methods, such as engineering software or manual calculations. If you can't, try to contact the author, John Sokolic, to ask about its accuracy and any known errors. Explore alternative short-circuit calculation tools that are well known and validated for accuracy. There are additional considerations. It's vital to understand the limitations and assumptions of any short-circuit calculation tool. Short-circuit calculations should always be done by qualified personnel. Actual short-circuit values may differ from the calculated ones due to things like system configuration and equipment tolerances. Always exercise due diligence when performing calculations with any software package. Understand the underlying assumptions behind the methods used. Make sure that you use real-world data for your calculations. Real-world data would be things like the actual transformer impedance, conductor sizes, and lengths. These values must be accurate for a short-circuit study to provide accurate results. Firstly, focus on gathering accurate input data. Secondly, understand the tool's limitations. Thirdly, cross-validate with alternative methods. It's crucial to recognize that software is a tool, not a replacement for sound engineering judgment. Short-circuit studies are essential for electrical system design and safety. They determine the magnitude of fault currents, which helps in selecting appropriate protective devices like circuit breakers and fuses. These devices must be capable of interrupting the maximum available fault current to prevent equipment damage, fire hazards, and electrical shocks. There are several methods for performing short-circuit calculations. One common approach involves manual calculations using Ohm's law and per-unit impedance methods. However, for complex systems, specialized software tools are preferred due to their ability to handle large amounts of data and perform iterative calculations efficiently. When performing short-circuit calculations, several factors need to be considered. These include the system voltage, transformer impedance, conductor impedance, motor contributions, and fault impedance. The system voltage is the nominal voltage of the electrical system under consideration. Transformer impedance represents the opposition to current flow within the transformer. Conductor impedance is the opposition to current flow within the conductors. Motor contributions refer to the fault current supplied by motors connected to the system. Fault impedance is the impedance at the point of the fault. Several industry standards and guidelines provide guidance on performing short-circuit calculations. These include the Institute of Electrical and Electronics Engineers Standard 241, commonly referred to as the Buff Book, and the National Electrical Code, also known as NEC. The Institute of Electrical and Electronics Engineers Standard 241 offers recommended practices for electric power systems in commercial buildings. The National Electrical Code provides requirements for electrical installations, including short-circuit protection. When evaluating the results of short-circuit calculations, it's essential to compare the calculated fault currents with the interrupting ratings of the protective devices. The interrupting rating of a protective device is the maximum fault current that the device can safely interrupt. If the calculated fault current exceeds the interrupting rating of the protective device, the device may fail to interrupt the fault, leading to equipment damage or personal injury. In addition to selecting protective devices with adequate interrupting ratings, it's also important to coordinate the protective devices to ensure selective tripping. Selective tripping means that only the protective device closest to the fault should trip, while other devices upstream remain closed. This minimizes the extent of the outage and allows for faster restoration of power to unaffected areas. Short-circuit calculations are typically performed during the design phase of an electrical system and should be updated whenever there are significant changes to the system. Changes that may warrant a new short-circuit study include adding new equipment, modifying the system configuration, or changing the utility source. It's also important to document the assumptions and methodology used in the short-circuit calculations. This documentation should include the System 1 line diagram, equipment data, and calculation results. The documentation should be readily available for future reference and review. There are many software packages available for performing short-circuit calculations. Some popular software packages include EasyPower, SKM Power Tools, and ETAP. These software packages offer a range of features, including automatic data entry, fault current analysis, protective device coordination, and arc flash hazard analysis. The choice of software package depends on the specific needs of the user and the complexity of the electrical system. When using software for short-circuit calculations, it's important to verify the accuracy of the results. This can be done by comparing the software results with manual calculations or by using a second software package to perform the same calculations. It's also important to understand the limitations of the software and to interpret the results accordingly. Short-circuit calculations are an essential part of electrical system design and safety. By understanding the principles of short-circuit calculations and using appropriate tools and methods, it's possible to ensure that electrical systems are properly protected against fault currents. This helps to prevent equipment damage, fire hazards, and electrical shocks, creating a safer environment for people and property. The accuracy of short-circuit calculations depends on several factors, including the accuracy of the input data, the validity of the calculation methods, and the proper use of software tools. It's important to use accurate data and appropriate methods to ensure that the calculation results are reliable. Short-circuit calculations are not an exact science. There are always some uncertainties involved, such as variations in equipment tolerances and system operating conditions. Therefore, it's important to use engineering judgment when interpreting the calculation results. The results should not be treated as absolute values, but rather as estimates of the potential fault currents. These estimates can be used to make informed decisions about the selection and coordination of protective devices. In summary, short-circuit calculations are a critical aspect of electrical system design and safety. They help to determine the magnitude of fault currents, which is essential for selecting appropriate protective devices and ensuring selective tripping. By following industry standards and guidelines and using appropriate tools and methods, it's possible to perform accurate and reliable short-circuit calculations. This contributes to a safer and more reliable electrical system. When performing short-circuit calculations, it's essential to consider the impact of different fault types. The most common fault types are three-phase faults, line-to-line faults, and line-to-ground faults. Three-phase faults involve a short circuit between all three phases of the electrical system. These faults typically result in the highest fault currents. Line-to-line faults involve a short circuit between two phases of the electrical system. Line-to-ground faults involve a short circuit between one phase and ground. The magnitude of the fault current depends on the type of fault and the impedance of the fault path. It's important to consider all possible fault types when performing short-circuit calculations to ensure that the protective devices are adequately sized to interrupt the maximum available fault current. In addition to fault types, it's also important to consider the location of the fault. Faults can occur at various points in the electrical system, such as at the transformer, at the bus, or at the load. The fault location affects the magnitude of the fault current and the voltage drop at the fault location. It's important to perform short-circuit calculations for various fault locations to determine the worst-case fault conditions. This ensures that the protective devices are properly coordinated to protect the entire electrical system. When performing short-circuit calculations, it's also important to consider the impact of motor contributions. Motors connected to the electrical system can contribute fault current during a fault condition. The amount of fault current contributed by a motor depends on the size and type of motor, as well as the motor's operating conditions. It's important to include motor contributions in the short circuit calculations to accurately determine the total fault current. Failure to consider motor contributions can result in underestimation of the fault current, which can lead to inadequate protection of the electrical system. In addition to considering motor contributions, it's also important to consider the impact of distributed generation sources. Distributed generation sources, such as solar panels and wind turbines, can also contribute fault current during a fault condition. The amount of fault current contributed by a distributed generation source depends on the size and type of generator, as well as the generator's operating conditions. It's important to include distributed generation contributions in the short circuit calculations to accurately determine the total fault current. Failure to consider distributed generation contributions can result in underestimation of the fault current, which can lead to inadequate protection of the electrical system. Short circuit calculations are a complex and challenging task. It requires a thorough understanding of electrical system theory, as well as familiarity with industry standards and guidelines. It's important to have qualified personnel perform short-circuit calculations to ensure that the results are accurate and reliable. The calculation should be reviewed and updated regularly to reflect changes in the electrical system. By following these guidelines, it's possible to ensure that electrical systems are properly protected against fault currents. This helps to prevent equipment damage, fire hazards, and electrical shocks, creating a safer environment for people and property. When reviewing short-circuit calculation reports, pay close attention to the assumptions used. Assumptions about source impedance, cable parameters, and equipment ratings can significantly impact the results. Be sure these assumptions are valid for your specific system. Examine the calculated fault currents at various points in the system. Compare these values to the interrupting ratings of the circuit breakers and fuses. Ensure that the protective devices are adequately rated to handle the maximum available fault current. Verify that the protective devices are coordinated properly. This means that the device closest to the fault should trip first, isolating the faulted section of the system while leaving the rest of the system operational. Look for any potential over-duty conditions. An over-duty condition occurs when the calculated fault current exceeds the interrupting rating of a protective device. If any over-duty conditions are identified, corrective actions must be taken, such as replacing the over-duty device with one that has a higher interrupting rating. Review the arc flash hazard analysis. This analysis estimates the potential arc flash incident energy at various locations in the system. The results of this analysis are used to determine the appropriate personal protective equipment that workers must wear when working on or near energized equipment. Ensure that the arc flash hazard analysis is up to date and accurate. Changes to the electrical system can affect the arc flash hazard levels. Therefore, it's important to update the analysis whenever changes are made to the system. In addition to reviewing the short-circuit calculation report, it's also important to conduct a field verification of the results. This involves measuring the actual impedance of the electrical system and comparing the measured values to the values used in the calculations. This helps to identify any discrepancies between the calculated and actual values. If significant discrepancies are found, the calculations should be revised to reflect the actual system conditions. Short-circuit calculations are not a one-time event. They should be performed regularly throughout the life of the electrical system. The calculations should be updated whenever changes are made to the system, such as adding new equipment or modifying the system configuration. Regular short-circuit calculations help to ensure that the electrical system is always properly protected against fault currents. This helps to prevent equipment damage, fire hazards, and electrical shocks, creating a safer environment for people and property. When selecting a short-circuit calculation software package, consider the following factors. The software should be user-friendly and easy to learn. The software should be able to handle the complexity of your electrical system. The software should comply with industry standards and guidelines. The software should provide accurate and reliable results. The software should offer a range of features such as automatic data entry, fault current analysis, protective device coordination, and arc flash hazard analysis. Before purchasing a short-circuit calculation software package, it's a good idea to try out the software with a trial version. This allows you to evaluate the software's features and performance before making a purchase decision. It's also a good idea to read reviews of the software from other users. This can provide valuable insights into the software's strengths and weaknesses. After purchasing a short-circuit calculation software package, it's important to attend training courses to learn how to use the software properly. This will help you to get the most out of the software and ensure that you are using it correctly. It's also important to keep the software up to date with the latest versions. Software vendors often release updates to address bugs and improve performance. Keeping the software up to date will help to ensure that you are using the most accurate and reliable version of the software. In conclusion, short-circuit calculations are a critical aspect of electrical system design and safety. By following industry standards and guidelines, using appropriate tools and methods, and having qualified personnel perform the calculations, it's possible to ensure that electrical systems are properly protected against fault currents. This helps to prevent equipment damage, fire hazards, and electrical shocks, creating a safer environment for people and property. Always double-check any calculations before committing to a final design.